Okay, hey everyone. My name's Noah Johnson. I'm going to talk about privacy-preserving smart contracts. A bit about myself. I'm a PhD student at UC Berkeley, and also co-founder and chief product officer at Oasis Labs, which is a company building a smart contract platform based on some of the research I'm going to talk about today. So let's start with a brief history of blockchain. So of course, blockchain became popular in 2009 with the introduction of Bitcoin. Later, Ethereum came along and introduced the concept of smart contracts and showed how to run general purpose computations in a distributed way. And then recently, we've seen the rise of new sorts of applications, including games, like CryptoKitties. CryptoKitties is interesting because it's the first blockchain application that really went mainstream. Unfortunately, CryptoKitties also exposed cracks in our current infrastructure. When CryptoKitties was popular last December, it caused major congestion in Ethereum. It caused transaction costs to go through the roof. So this is where we are today, and there's a question of, what do we have to look forward to in the future? If you're bullish about blockchain, which I hope everyone here is, then you'll agree that in the future, blockchain will power a set of applications that are significantly more complex than CryptoKitties and anything that we've seen so far. These are applications that people get excited about when they talk about blockchain and its revolutionary potential. Things like credit scoring, medical diagnostics, private auctions, and so forth. And so my talk today is going to focus on what are some of the challenges for supporting these applications and what are requirements of the underlying infrastructure in order to address some of those challenges. Just a quick teaser, you'll notice here that all of these applications require a lot of computation, and they all require a lot of data, and oftentimes the data is sensitive. So let's start with a concrete example to sort of motivate the challenges. This is a credit scoring application. So in this application, you have a number of institutions that contribute their data into a smart contract, which is designed to train a machine learning model with that data. And of course, this runs on workers or miners that are part of the underlying platform. And the smart contract might output a model from this training data. There are variations of this. Maybe the model would be stored inside the smart contract, and the smart contract would expose a way to query the model. But the challenges are the same either way. So this is great. It's a great use of blockchain in that all of these institutions know that if they do this with a smart contract, the data will only be used for the purpose of training this credit scoring model. And users who may want to apply for a loan based on this model have visibility into how their data is used and how the model is trained. So this is ideal. Unfortunately, if you tried to build something like this on today's platforms, you would face a number of issues that essentially make these sorts of applications a non-starter. The first issue is that, of course, the data is very sensitive, and so there's nothing stopping workers that actually run the smart contract from stealing the data. Even if you trust the workers not to steal the data, there's also this risk that when you're training a machine learning model on sensitive data, the output model itself might leak information about the inputs. Now you might think, well, clearly a machine learning model is already private, right? And hopefully by the end of this talk, I'll convince you that that's not the case. And then the final challenge, of course, is that today's blockchains just fundamentally aren't designed to scale to complex workloads like machine learning. Already, we saw CryptoKitties. Even though the breeding algorithm in CryptoKitties is not that complex, even something like that, significantly slowed down the entire Ethereum network. So fundamentally, those platforms are not going to be able to accommodate these sorts of more advanced use cases. So each of these problems actually requires a solution at different layers of the stack. And so I'll talk about solutions for each of these. At the layer of the workers, that is the risk of the machines that run the smart contract leaking sensitive data, we have a technique called confidentiality-preserving smart contract execution. At the layer of the application, and specifically the risk of data leakage through the result of the computation, we have a class of techniques called privacy-preserving analytics and machine learning. And then finally, at the infrastructure level, we have some new design that allows for more scalable smart contract execution for significantly more complex types of smart contracts, not just simple transactions, which is the focus of much of the work in this space. So this requires a top-to-bottom approach, from the application layer all the way down to the infrastructure, and we'll see to the hardware layer. In this talk, I'm not going to talk about scalability. This is, of course, a hot topic in this space. There are a lot of projects that are looking at how to build more scalable platforms. Given this is the Zero Knowledge Summit, I'm going to focus on the privacy-related problems. So I'll talk about confidentiality and privacy. So the first one, confidentiality preserving smart contracts. So the basic abstraction of a smart contract, of course, it's a piece of code that takes some input and the current state, and it runs the code on that input and outputs a new state, which is recorded back to the ledger. The abstraction of a confidentiality preserving smart contract is that all of these inputs and outputs are encrypted. That means that nobody can see the data, not even the workers that are executing the smart contract. Now, given that no one can see the inputs and outputs, it's essential that the system provides a way for the workers to prove that the execution result is correct. And we saw how this works, for example, for zero knowledge proofs, where essentially zero knowledge allows you to run all of the computation locally and only output this proof. But the more general version of this problem is you have some piece of code, the data is sensitive, you can't rerun the computation locally yourself to convince yourself that the result is correct, right? Because the data is secret. And so we need schemes that allow proving that the result is correct, even if you can't see the underlying data. So it turns out there are a number of different technologies that can be used to implement confidentiality preserving smart contracts. And these can be kind of broadly categorized into hardware-based approaches and crypto-based approaches. So the challenges of these cryptographic approaches like multiparty computation, zero-knowledge proofs, and homomorphic encryption is that they tend to be very slow. They incur often orders of magnitude performance overhead compared with native computation. And so one of the research goals for our platform is actually to combine these different techniques together to allow the developer to choose which application makes sense, because each one has different trade-offs in terms of the performance and the classes of applications that it can support. In this talk, I'll focus specifically on secure hardware because we've heard many discussions on really exciting new work for some of these other techniques. So secure hardware is a technology, there's various implementations of this, but the fundamental abstraction is what's called a trusted execution environment, also known as an enclave. And an enclave essentially is a piece of technology that allows an application to run in a protected way. So an enclave provides two important security properties. The first one is that it guarantees that the operating system and other applications can't modify or tamper with the execution of the application inside of the enclave. So this is what we call integrity. It means that the computation result is guaranteed to be correct. The second property is confidentiality. So this means, again, that the operating system and the applications, as well as even the user of the machine, can't actually inspect the state of the execution, including the code and the data. And secure enclaves also provide what's called remote attestation, so the hardware can generate a proof, essentially, of the contents of the enclave, where that proof can be verified by a remote party, even if they don't have physical access to the machine, to prove that the right code was running inside the enclave and that the entire thing was running on authentic secure hardware. So essentially, you can think of secure enclaves as a black box that can't be viewed or tampered with, even by the operating system, the hypervisor, and the user of the machine itself. So you might notice actually that this property of integrity, that is guaranteeing that when an application runs on a remote machine, the execution result is correct, actually is very similar to some of the goals of smart contract platforms. It turns out that both of these technologies actually have similar goals. They both try to run a piece of code in a way that achieves certain properties. And they do this in very different and complementary ways. So smart contracts and platforms like Ethereum, of course, they guarantee integrity just by virtue of the consensus protocol that's used. Also, they have strong availability and persistence because they are replicated and decentralized and store state immutably on a distributed ledger. But today's smart contract platforms don't provide any confidentiality. Now, trusted execution environments also provide integrity that's enforced by the hardware. On the other hand, they provide no availability or persistence, right? You can just turn off the machine and you lose all the state that's running. But they do provide confidentiality. So if we can combine these different technologies together, essentially we can get the best of both worlds. And that's exactly what we did in a recent research paper called Akedan. So this was a collaboration between Berkeley, Cornell, and UIUC. And in this paper, we show how to combine secure hardware with blockchains in order to essentially endow smart contracts with confidentiality. So the key idea is to execute the smart contract itself inside of this secure enclave and then store the state back to blockchain in order to get persistence. So getting this all to work is actually quite a bit more complex than you might think. You need to separate the execution from the consensus because secure enclaves have no internet connectivity. You need to design new cryptographic schemes to prevent replay attacks and rollback attacks. So there's a lot of interesting details. I encourage you to check out the paper if you're curious about that. In this paper, we implement several different applications that show the advantages of being able to keep smart contract state secret. We also ported an EVM to run inside the enclave so that any existing Ethereum smart contract can immediately benefit from confidentiality. And to demonstrate this, we ran the actual CryptoKitties breeding algorithm inside the enclave. So this is a good example, actually, of the advantage of keeping state secret. The developers of CryptoKitties actually intended to keep the breeding algorithm secret. They obfuscated it and didn't release the source code. But because on Ethereum, of course, even the bytecode is public, then people were able to reverse engineer it and sort of game the system in order to increase their likelihood of breeding valuable cats. So this is really promising. It suggests that trusted hardware could be used as a primitive for secure computing, not just for blockchains, but for general computations. In particular, secure enclaves provide a number of strong security properties, including the ability to authenticate the hardware itself, the ability to authenticate the device, and to guarantee the integrity and privacy of the execution, even for executions that run on remote machines. So this could become a platform for building new security applications. And there's actually several recent research projects that show how to use secure enclaves for cloud computing. These aren't specific for blockchain, but they are solving a very similar problem. And actually all hardware manufacturers, or at least the major hardware manufacturers, recognize the importance of this problem. So they've all shipped versions of secure hardware in their recent chipsets. Most notably and well known is Intel secure software guard extensions, but NVIDIA and AMD have shipped secure hardware as well. Now, not all of these provide the core features I described earlier. For example, AMD's version only guarantees confidentiality. It doesn't guarantee integrity. But this is clearly the direction that the industry is moving. But there are still major challenges. So all of the secure computing techniques I described earlier, including the cryptographic techniques, all have different trade-offs in terms of the adversary model. And this is true of secure hardware as well. So what I described earlier, those properties are, of course, properties of the abstraction. Those are ideal properties of a secure enclave. In practice, of course, there's no such thing as a perfectly secure system. It's a matter of trade-offs. And so there are some open questions of how secure can secure hardware be and under what threat models. An interesting thought experiment is, what would you entrust to run inside one of these secure execution environments? Your Bitcoin keys, your financial data, your health data. You probably are already using some version of trusted hardware if you use a hardware-based wallet, right? And you can see the advantage of having a hardware-based mechanism to protect the sensitive material, in this case, your Bitcoin keys, which means that even if your machine is infected with malware, unless someone has physical access to the machine or to the device, they're not able to steal your keys. And so in some sense, secure enclaves are just a generalization of that concept. And of course, you could layer these other secure computing techniques onto secure enclaves to provide additional security. Like you could run multi-party computation inside of an enclave, because multi-party computation has a different threat model that is complementary to secure enclaves. Multi-party computation assumes that multiple parties aren't going to collude and share answers, whereas secure enclaves assume that someone can't physically tamper with and break the key properties of the hardware device. So one of the research directions of Oasis is how can we do even better than what we have today in terms of the security. And so in order to get there, let me list out what we think are the key properties of a secure enclave. The first and most important is that it needs to be an open source design. So everything in the blockchain space, of course, is open source. And so to the extent that you're relying on hardware for any part of the security or integrity of the platform, the hardware itself had better be open source as well. And there are advantages to having the hardware be open source. That means that it's more transparent. It allows other researchers and security experts to audit the design. It's more amenable to formal verification. And so unfortunately, and as well as secure supply chain. So if it's open source and in the public domain, then any chip maker can actually tape out one of these secure hardware chips. And so today's secure hardware technologies actually don't provide this property. But we're working on a project that does. So there's this ongoing project called Keystone, which is a fully open source design for secure hardware. And this is a collaboration between Berkeley and MIT, and they expect an initial release in fall 2018. The Keystone design is based on the RISC-V microarchitecture, which was developed out of Berkeley. And the nice thing about building on top of RISC-V is that it's already widely adopted in industry. And so the plan for this project actually is to have an initial release in the fall that runs on FPGAs, and then a release later, I think early next year, that actually runs on an existing RISC-V chipset. Last week, we actually had a workshop at UC Berkeley that brought together industry and academic leaders in secure enclaves. And the workshop was specifically focused on kind of open challenges in building a fully open source secure enclave. So that was exciting. Okay, so that concludes the first part of my talk, where I talk specifically about techniques for securing the computation. Now, assuming that we've secured the computation so that workers can't leak data, now the natural application for smart contracts is let's do things with sensitive data, because now we have assurances that the workers can't leak data. And so now this brings in a completely different set of challenges related to how do we safely use sensitive data in such a way that smart contracts can do useful things with the data, but we can still guarantee the privacy of the users in the original data sets. And I want to discuss this briefly because I think it's a problem that is still, at least today, less understood in the community. So I'll discuss the challenges in a general way, but hopefully you can see how these apply directly to a lot of the smart contract applications I listed earlier. So to motivate privacy risk, let's suppose we have a data set of trips, right? And on the one hand, we have an analytics question that asks how many people visited New York last year, and on the right, we have a question that asks how many trips did Joe take last year. So clearly, the question on the left is safe, right? It doesn't violate anyone's privacy, whereas the question on the right very clearly violates Joe's privacy. Now, these questions are asked of exactly the same data, right? The only difference is specifically what type of question was asked and what information is revealed in the answer to that question. And so there's sort of a broader question here. How do we reason about the difference between these two queries? The fact that this one is sort of intuitively safe and non-privacy violating, and this one very clearly violates privacy. And how do we, these are two extremes, but how do we kind of bridge the gap and reason about something in between? And in addition to kind of formalizing this, there's a question of how do we build a system that can automatically allow things that are safer and protect against things that are less safe? So I want to point out that actually this isn't an access control problem. This is not a problem of just restricting access to certain portions of the data, because again, both of these queries run on exactly the same data set. And again, the only difference is what specific question is asked of the data. So that's privacy risks for statistical queries. You also need to be very careful when training machine learning models on sensitive data. So one example, and there's a paper that illustrates this, is training a deep learning model on some email training data that had social security numbers and credit cards. And this paper showed that actually an adversary can query the output model in order to reconstruct the original input data, credit card numbers and social security numbers, strictly from the model itself. And in other work, people showed how to, if you know properties of one person's data, it's very trivial, given the model, to determine whether that member was part of the original training data or not. And one more example is, here on the right, the left is an image that was reconstructed from an image classifier model that was trained on an image on the right. Okay, so clearly there are major privacy risks, even for things that seem innocuous, like statistical queries and machine learning on sensitive data. What people have done today, the state-of-the-art technique for addressing these problems is called data anonymization. And how data anonymization works essentially is scrubbing fields in the data that could reveal individuals. And there are different versions of this. The basic idea is, of course, names could identify people. IDs oftentimes can be linked. So we're going to mask that data. Certain information we might bucket so that it's more coarse, right? So that there are fewer distinct values, and so forth. And so once we've done this process, then this is the data set that would be released for analytics. So this might seem good on the surface, right? We've removed PII. We've masked any information that could be used to identify individuals. Turns out there are actually a few problems with this. The first is that the process of anonymizing data actually skews the results of analytics on the data, even analytics that would otherwise be safe. So for example, if a doctor is training a model for detecting the risk of high blood pressure, if this is what the actual result is, then anonymizing the data set may very well produce a result like this. And the reason for this phenomenon is that the process of anonymizing the data is very blunt, right? It doesn't take into account specifically what's being done on the data. And an example like this, actually all the users would prefer probably that this particular model was trained on the original data set, right? Because it clearly doesn't harm any of their privacy, and all of them benefit by a more accurate result. Okay, so that's one problem. The second problem actually is that anonymization is ineffective. So oftentimes an adversary can take an anonymized data set and combine it with other outside information in order to re-identify individuals in the data set. And this isn't just a theoretical attack. Actually, there are a few high-profile examples of exactly this type of attack. So the Netflix prize, does anyone remember the Netflix prize? Netflix released anonymized records of customer movie ratings, and they had this contest for data scientists to train better recommendation models for movies. And so they anonymized the data set according to best practices and released it to these researchers. Someone showed how to take movie ratings on IMDb and link those to records in the original data set in order to re-identify certain individuals. In another more recent example, New York City released anonymized taxi logs, and a security researcher went to celebrity gossip blogs and found pictures of celebrities getting into taxis, and then from those pictures it was trivial to link those rides to the original data set, right? Because he knew exactly what time they got in and from what location, and so he could figure out where they went and how much they tipped. So the point here is, who knows what other data is out there, right? And if you're relying on anonymization to protect privacy, you don't know what data set might be out there, either today or in the future, that would allow someone to do these sorts of attacks. So this is not a viable solution. Turns out there is a better solution, and it's called differential privacy. So I'll discuss this kind of at a conceptual level. This is actually backed by rigorous math, but I'll try to give you an intuition for how differential privacy works. The basic definition says that if you have any two databases that differ only in one user's data, so for example, Joe is in database 1 but not database 2, differential privacy says that any query you run on those data sets, or in our setting, any smart contract, the output against those two databases had better be essentially the same. In other words, there can be no way from the results to tell which of these databases was used to run the query. So this means there's no way to tell whether Joe was in the data set or not. So the differential privacy actually says that this has to hold true for every user and every data set. And so this is nice because it aligns very well with kind of our intuitive notion of privacy. That is to say, this guarantees that while I might be comfortable allowing my data to be used for some purpose, I don't want whatever you're doing with my data to be able to identify my record, or even whether I was in the data set or not. If you look in the literature, the formal definition is parameterized by what's called a privacy budget. So the nice thing about differential privacy is that because it's so general and such a strong definition, it means that from a user's perspective, if they know that differential privacy is enforced, they don't need to worry about specifically what computation is running, right? As long as this property holds, it doesn't matter what this query is doing. Now, the user might want to know anyways, but from their perspective, as long as the system can guarantee that this property holds, there's no downside to the user contributing their data. So they had better contribute their data anyways because the results would be the same. And so this is a nice definition, especially for blockchain. The problem is that it's just a definition. And so most of the previous work in this space is largely either theoretical or focuses on very specific applications. So Google actually uses differential privacy to track website visits in Google Chrome, and Apple uses it to track statistics about emoji use on iOS. So outside of these limited domains, there still today is no general purpose system for enforcing differential privacy automatically. So this was the subject actually of my dissertation, is building a framework to automatically enforce differential privacy for general purpose queries in an automated way. And so in the interest of time, I'll skip over some of these details. I want to point out, first of all, that the system is already deployed internally at Uber. So all internal queries that are submitted by data analysts at Uber actually go through this system to enforce differential privacy. And other companies are starting to deploy it as well. And the entire thing is open source, so it's available on GitHub. So the idea is to integrate some of this work into the application layer, the development layer for smart contracts, so that developers who are building new smart contracts on sensitive data don't have to be security experts in order to build smart contracts that are, by definition, private and preserve privacy. In Followon work, we showed how to build a system to automatically enforce differential privacy for machine learning models. So a data scientist defines a machine learning pipeline. The system automatically converts it into a new pipeline that, when trained on sensitive data, automatically enforces differential privacy. The nice thing about machine learning actually is that differential privacy is a very good fit for machine learning, because the goals of machine learning, of course, are not to overtrain on any individual's data. So by satisfying differential privacy, actually, it turns out, in certain cases, you can produce a more robust model that is more resilient against overtraining. Because that's exactly the property that is trying to be addressed by differential privacy. That is, the output can't be overly influenced by any individual's data. So I talked about this as a top-to-bottom approach. Now you understand a little bit more about confidentiality-preserving smart contracts and privacy-preserving smart contracts. We think the combination of those properties together with increased scalability is useful for a wide range of different applications that fundamentally can't be built today on platforms like Ethereum. So here's a list of some of them. In a collaboration between Berkeley, ETH Zurich, and Stanford Healthcare, there's already an application that is built using this technology called Cara. So Cara is trying to solve this problem that today a lot of medical data is locked in these data silos, so it's underutilized. And the data is extremely valuable for research purposes, but of course the data is very sensitive, so oftentimes users and doctors are reluctant to share the data. And so Cara essentially is a data market that's built on blockchain that allows patients to input their data. In the current version, they scan it or input it with a mobile app. That gets stored in a smart contract. Researchers who want to train models on that data can pay tokens, and the smart contract will automatically train their model on the data. And the users get tokens in compensation for contributing their data, and the researchers get as output the trained model. So the nice thing about this, number one, is with confidentiality preserving smart contracts, users and researchers have assurances that even the workers that are helping to train these models won't be able to view or leak the data. And with differential privacy, right, patients don't have to worry about exactly what kind of model is being trained. They know that there's no way from the model that a researcher could even identify them. And of course, the importance of scalability if you want to do something like machine learning and have this scale to, millions of users and so forth, and you want it all to run on-chain without having to resort to off-chain solutions, for example, because you want to integrate with tokens, then it's important to have a platform that can scale to these sorts of more sophisticated workloads. So that's Cara, and that concludes my presentation. Thanks.
Are there any questions? A couple. Cool.
Hi. Thanks for the talk. I'm wondering if you can talk a bit more about where you see data living, kind of like in its stagnant state, whether that's encrypted, whether it's on users' own personal devices. To me, the idea of just data, like personal data on a blockchain, doesn't really make sense. I don't see, like we have strategies for sharding, great, but ultimately data is something that should only ever live on devices of people who actually need it. And so if you can just talk a bit about how you think about where data just resides in more of a stagnant state in these kinds of models.
Yeah. So of course, when the data's at rest, it needs to be encrypted if it's stored remotely anywhere, right? That's just a fundamental property of security. What I described doesn't presume necessarily that the sensitive data is stored directly on the blockchain. So the platform, in practice, the system provides flexibility for storing the data wherever users are comfortable with. And the smart contract has a way to ingest data from different data sources. So the platform can integrate with distributed data stores. It could allow users to directly send their data when they call into the smart contract. They could allow it to be stored on the blockchain, but there are other reasons why you might not want to do that. Scalability reasons in addition to privacy.
Back here in the back, hey.
Yeah.
When you were talking about the secure enclave, you had mentioned the smart contract executing inside of the secure enclave, and then you mentioned that that secure enclave would be offline. How would the results of that computation end up communicating back to an on-chain event in the case that it's offline?
Yeah, so there's software that runs outside of the enclave that is responsible for constructing the enclave in a secure way and getting the encrypted data into the enclave. Once the enclave finishes executing, it returns the results, up the stack to the software that's running in the untrusted space. But the results are encrypted inside the enclave, so it's only the encrypted results that are sent back. And so the code that's inside the enclave doesn't have network access, but the worker that is actually running the computation runs some code in the untrusted space that is responsible for returning the results back to the blockchain.
So far as I remember, what I've read about secure enclaves, especially provided by manufacturers like Intel, it was required to have some sort of collaboration with Intel about using the secure enclave with a certification or some process in place. Now, if you put that in an open source design and put it on the blockchain, wouldn't that be a very fertile ground for dark DAOs to arise and actually run maybe their own special version of a voting client inside that enclave in return for some ether that I get once I have the remote attestation that I voted in the way the dark DAO wanted from me?
So I'm not sure I fully understand the attack, but what you were describing earlier, yes, in Intel's current design, they are a central party that is responsible for verifying that enclaves are genuine and that these remote attestation certificates were produced by genuine hardware, because Intel is the one that embeds the private keys into the hardware. So Intel is the one that knows which private keys are valid for these signatures. As far as the attack on...
So the attack is actually pretty straightforward. So what could happen is that you promise someone to an ether if you vote on some whatever random system in his favor. And then the attacker provides you with a code that actually does the voting using your private key to actually authorize it, so that your private key never leaves your device. And then he makes sure that you run this code in an enclave, providing the secure attestation of the execution. And with that, you can prove that you voted in his favor, and he transfers the ether. And that's what's called a dark DAO. And you could use that as a perfect fertile ground to actually run these things.
So it sounds like what you're describing actually is sort of a more fundamental concern with any system that provides privacy.
Yeah,
right?
exactly.
In the same way that...
Not exactly any system, but when you use a secure enclave, you have virtually anything at your disposal to do whatever you want without being actually discovered by anyone. So you can actually trick any other system by actually building a network of colluders working together through secure enclaves. If you just put that on a public blockchain where everyone can just incentivize to run any smart contract in that enclave. And as far as I know, the only reason why this isn't happening already is that, and that is where my knowledge ends, is that there is some sort of verification by the hardware manufacturer before you actually have access to that enclave. I learned that from that hardware wallet, what's it called? The only one that actually uses an enclave at the point.
Yeah, so I mean that's sort of an application layer concern, right? And that could be mitigated with some
Yeah.
sort of stronger identity system. What you just described is actually not a failure of the platform.
No,
that's
it's
more
not.
collusion
It's not.
by right.
Yes. Do you have any ideas how to prevent that from happening? Because you don't want to introduce a trust model where you have to have someone certify your smart contract that is executed in your enclave. Right? Because you want it permissionless.
Depending on the specific application, there's potentially mitigations for that. I think what you're describing, again, is a sort of a fundamental property of any system that guarantees privacy and security, right? In the same way that, anonymous cryptocurrencies allow people to launder money without being traced, right? That doesn't mean that the technology is inherently flawed just because there are certain bad use cases that are enabled by strong privacy guarantees.
I actually got to wrap. This session's done. So, sorry. I know that there's a few more questions, but maybe, do you want to stick around just outside if there's more questions? Cool. Thanks, guys. Thank you.